Welcome everybody, Mr. Allen here. I'm just going to go through a few examples here showing how to solve factorial equations. Our factorial equations will sometimes come from permutations or combinations as a starting point, and so we want to remember that this is how a permutation is calculated. When you have something like 10 items and we want to permute 6 of them, or we want to place 6 of them, this is the actual calculation that happens. Now, often you'll just use a calculator, punch it in, and not know where that number came from, but this is the basic idea. It's the number of ways all the items could be organized divided by essentially those that we don't want. So if it's 10 permuted 6, it's 10 factorial on top divided by 10 minus the 6, so 4 factorial on the bottom. So essentially those bottom 4 things get divided out and are left off the list. Combinations are similar, except that we're doing the second division that eliminates all the duplication of organizing things. So in a permutation, of course, order matters. In a combination, the order doesn't. And so that second division, that R factorial there, is taking out all of the duplications. So just sort of getting into it here, the first question says 6 permuted 4 times. So our first equation here is a permutation 6-4 equal to 2x. Essentially all we're going to do on these questions is get the equation down and then rearrange it as much as possible. Well, expand the factorials, I should say, and do some simplification and then rearrange as needed. So here, again, based on what we saw above, P64 is 6 factorial divided by 6 minus 4 factorial. And so as we kind of go through that, if we expand it out just to sort of make sure we understand exactly what we're seeing here, it's 6 times 5 times 4 and so on top. And 6 minus 4 is simply 2 times 1 on the bottom. Sorry, in my numerator and my denominator. Let's use proper math speak here. And then basically my 2, 1 divides out from the numerator and denominator, and I have this left over. 30 times 12 is 360 equals 2x, and then of course we can solve that pretty easily by rearranging as we did many years ago. So really here the only thing that's in any way new to us is sort of understanding how a P64 expands or is actually calculated, and then expanding out the factorials in order to do the divisions, simplify from there. Now I've got some numbers and I can work it out. Now, obviously, I guess the first thing is right off the bat, you could have punched P64 into your calculator and got the answer 360 right off the top. But what we're looking to do here is understand how it expands so that when we have something like we see here in the second question, something where we can't simply go straight to the calculator, we can still do that. So here we're looking at n factorial over n minus 2 factorial. If I'll just try to pull this out and then cover it back up for a moment. So again, n factorial in the numerator, n minus 2 in this case factorial in the denominator, equal to the 42 that was already there. And then exactly the same thing. N factorial is n times n minus 1 times n minus 2 and so on all the way down to 1. Okay, so if 6 factorial was 6 times 5 times 4, each of those numbers is 1 smaller than the previous. Same sort of thing here. N is whatever value it happens to hold, and then n minus 1 is 1 number smaller, n minus 2 is 2 numbers smaller, and so on. N minus 2 factorial is our starting point here. And then 1 smaller than that is n minus 3, and then n minus 4, and so on. Now, not knowing exactly what those values are, oh, that's not going to work for me. Not knowing exactly what those values are, we do have sort of a series of values all the way down to 1. But it doesn't really matter what they were because we have the same series of values in the numerator as in the denominator up to the n minus 2. And so again, all those values will divide out. And I'll be left with n times n minus 1 equal to 42. That's something that we worked with back in grade 10 generally. So n times n is n squared, n times -1 is negative n. Subtract the 42 from both sides, and I'll end up with n squared minus n minus 42, which is something I can factor and solve that way. Now, last sort of thing to understand here, I sort of left myself a note so I wouldn't forget. When we get to the end and we find that n could have been 7 or n could have been -6 to start, we want to understand that n being -6 is impossible. Our original question said we have a certain number of items and we're going to basically place or organize 2 of them on a shelf in whatever it happens to be. So we couldn't have had -6 from the start. That just doesn't make sense. The idea of having -6 items and taking 2 of them and putting them in some kind of order doesn't make sense. So our permutations, our combinations, because of sort of what they represent, will never be negative values. Now we'll solve it normally. We'll get down in this case to the point where we have potentially 2 answers. But if one of them is negative, we cannot use it. Same sort of thing here, P2N1, so nothing really different from this question, with this question from the previous one. So kind of race through it here. I have 2n in my numerator, so 2n is the first term, 2n minus 1 is the second term, 2n minus 2. Again, exactly whatever this number is, 1 smaller goes to the next in the next spot, 2 smaller in the next spot, all the way down to 1. Similarly in the denominator, 2n minus 1, 2n minus 2, and so on. And so we have everything other than the 2n being able to divide out. 2n is 50, n is 25. So those are the basics. Not sure why I did all examples involving permutations, but obviously if we had a combination here as well, we would do the same thing except make sure we have the second division in the denominator. Last thing, if we're trying to prove something, in the previous examples we were saying this is equal to this. Here the question says show or prove these 2 things are equal. So we can't assume they are, even though we know they probably will be. So anytime we have a proof to do, we'll always separate our solutions into a left side, right side situation. So my left side in this case is the P85 because it's literally on the left side of my equation. After I recognize that that's what I'm being asked to do, I'm going to work through that part and just see what I can do. So here again, the first example is using numbers with the idea that we want to see the steps that we're going to follow. So here, permutations 8, 5. So it's 8 factorial over 8 minus 5 factorial in the denominator, which simplifies to 8 factorial over 3 factorial. I could go further at this point and say, well, if I expand that out, I know that my values will divide out with the 3 factorial in the denominator. I'm going to leave it here for now just because I'm going to. And then if we do something similar with the right side, recognizing that it's a permutation with 7, 4, and it's 8 multiplied out front. I can work with the 7 factorial in my numerator, 7 minus 4 factorial in my denominator. That's 7 factorial over 3 factorial. And so I essentially have 8 times 7 factorial as numerators if I tried to line this up as 2 fractions being multiplied. 8 times 7 factorial, of course, is 8 factorial. So the reason I left this first side without actually going that extra step further is to explain that whenever we're doing a show or prove type question, all that's important is that I get to the exact same thing on both sides. So you can clearly see here that I have an 8 factorial divided by 3 factorial as one of the equivalent expressions on my left side. I have an 8 factorial divided by 3 factorial here as well. And it's just one of the various equal expressions that I have on this side. Because I can clearly see that I have the exact same expression on both sides, I can therefore state that because my left side is equal to my right side, I have therefore proven, and that's what that word is, it's proven, that's my signature saying proven, that these two sides are equal. Okay, so I'm trying to prove that combinations n r equals a combination n minus r. And so left side here is n divided by n minus r divided by r factorial. On the right side, now, I could try, obviously if there's more to be done there, I can do it, but there isn't really anything I can do here that's going to be super easy. I could think about expanding out n factorial and then dividing out somehow the n minus r's, but I would end up with pretty messy numerator here. So I'm just going to move forward. And this is one of the things that happens when you're doing any kind of a proof. You might start on one side and then jump to the other side and then maybe even come back and sort of do a little bit more, just depending on kind of what you can do and how scary it looks to do it. So in the right side here, I have combinations n and n minus r. So sort of wrote that out. The numerator again is the n factorial. The denominator, now again we have to sort of remember what our format is. It's n minus the second value, so this value minus this value, and this value factorials. So it's n minus the n minus r this time. Sorry here, n minus the n minus r as one of the factorials, and then this thing, the n minus r, as the second factorial. So it's this complete expression that is going to be subtracted in the first case and is going to represent the second factorial. And then we have to do a little bit of work with that, I guess. So I see n minus in brackets r, and so that's n minus n and n minus negative r. So n minus n and minus negative r is a plus r, which of course works out to be just a r factorial at that point. The n's are subtracting. And if we kind of scroll back, just barely can be squeezed on the page, n factorial over n minus r factorial times r factorial, of course, is the definition of combinations, and it is what I had on the left side. I have the exact same thing on the right side here, with the understanding that, of course, the multiplications in my denominator can be done in either order. And so that means that the left side right here is equal to the right side right here, and therefore this has been proven. So I'll stop there. I don't think I have any more examples anyways. There's nothing too fancy here other than to sort of understand how we expand a permutation or a combination. It's as much for interest's sake as anything else. Potentially in university you'll need to know that a little bit more. This year we don't need to do it too much, but sort of having that ability and sort of understanding proofs in general is pretty valuable.